Okay. So tell me, how your interest in physics started.
So mainly it started with taking it in high school,
I see.
AP physics courses, like
I see.
physics one, two, C. So I was just like, I found it really intriguing that motion can, be described
Hmm.
with principles and equations, and these principles hold true for like many systems.
Right, right.
So then, just upon researching physics, like looking around, I discovered quantum physics, like particle. And then I
Right.
realized that they don't follow the standard principles of classical mechanics. It's like this
Well,
whole
that's yeah. I mean, the historically we discovered classical mechanics first, and then quantum. But quantum mechanics is the actual rules of the universe. So it's probably more fair to say that somehow uh, the 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 rules of quantum mechanics get disguised when you get to larger things, rather than somehow smaller things don't follow the rules of classical mechanics. It's classical mechanics that doesn't follow does all the rules of quantum mechanics. It's the other way,
oh,
right?
okay.
We just
Mm,
because we happen to be meter sized, we tend to assume that classical mechanics is correct and quantum mechanics is somehow weird, whereas
yeah.
quantum mechanics is the actual rules of the universe. The
Okay.
universe is quantum in nature.
Okay,
And
that's really interesting. Yeah.
yeah, and it's uh it's classical mechanics where, because of the large sizes and the large number of particles involved, uh basically the quantum nature gets uh hidden. So but yeah.
Okay.
Yeah,
So
we shouldn't say what,
okay, so
classical,
the quantum nature like gets hidden
the quantum,
when looking.
but it's the quantum mechanics is the uh real universe. The universe is quantum in nature,
Okay, that's really interesting.
right? The
Yeah.
actual universe, the actual rules of the universe are quantum. You can get to classical mechanics if you had enough computational power and input the rules of quantum mechanics. You should be able to derive the rules of classical mechanics. You can't start
Oh,
with
okay.
classical
Yeah.
mechanics and get to quantum mechanics because yeah.
Yeah. Yeah. Okay.
So yeah, it's
Okay, so I was wondering if you can tell us some more about particle physics.
sure.
Um so
Okay,
that's
so the first thing to know is, like you were mentioning, it's the size of things. Okay, so
mhm.
the first thing that anybody who's studying classical mechanics should know is basically where does it uh, start to appear, and it starts to appear roughly about at the molecule atom size. Okay,
Mhm.
so molecule is if a human hair is like 100 microns, so you look at, you pluck your hair depending on whether you have fine hair or coarse hair, it's 10 to 100 microns. Okay, so that's 10 to the minus 5-ish meters,
Mhm.
right? You look at, if you were to rip your phone apart and take out the chips and look at them under a very fine microscope, the individual transistors are on the scale of 10 nanometers, so about 10 to the minus eighth meters.
Mhm.
And I mean, sorry, 10 to the minus, yeah, 10 to the minus eighth meters, right? And that's roughly 100 atoms, right? So 10 to the minus 10 meters is roughly an atom. So you're getting close to, so the size of transistors on modern, if you have an apple, you rip it apart, you take out the M1 chip, the size of individual transistors on that is on the order of 100 atoms. And an
Okay.
atom is roughly, yeah, and so those chips work on quantum principles. right? They're the transistors inside a chip. They work on quantum principles because that's where you start to encounter the quantum nature of things. As things gets bigger and bigger, the quantum nature uh, gets gets hidden. You
Mm-hmm.
don't see the quantum nature anymore.
Yeah.
So okay, so that's an atom, right?
Yeah.
10 to roughly 10 to the minus 10 meters. That's an atom. And if you were a 19th century physicist, you knew all about atoms. Okay,
Mm-hmm.
you had that dude with the beard. What's his name? The Russian dude with the beard, Mendeleev, right? So
Mendeleev.
Mendeleev,
Yeah.
right? Yeah, he writes out. He figures out atoms. He makes the periodic table. Everybody's very excited. 100 odd atoms basically make up the whole universe, right?
Yeah.
And their picture of atoms is, think of a snowball, right? You got a snowball or a cotton candy, or right, it's big blob of something,
Mm-hmm.
and so and then imagine a ball of cotton candy with raisins stuck on the outside. Okay,
Yeah.
that's your atom,
Mm-hmm.
and you can do cool things with atoms. You can heat up atoms. They start moving around, and if you heat them up a lot, electrons come out. So they knew
Mm-hmm.
that in the 19th century, and that worked. So if you shake a piece of cotton candy which has raisins stuck on the outside, the raisins will fall off, right?
Yeah.
That's electron emission in the 19th century.
Electron mission.
Okay,
Got it.
yeah. So this model, because they were British, they didn't call it the cotton candy model. They called it the plum pudding model. But
Mm-hmm.
you've heard of the plum pudding model, I'm sure.
Yeah, I've heard of it.
Right. Yeah. And it's a beautiful model. It works really well for, the stuff they were doing in the 19th century, which is, building steam engines and whatnot. If you heat something up, the electrons come off. If you get two of them together and one of them has too many electrons and one of them has not enough electrons, like sodium and chloride, boom, they attract each other, and they make sodium chloride, et cetera, et cetera. You can do ionic bonds, you can do uh, covalent bonds, you can do all sorts of cool stuff with just that model. You can do
Mm-hmm.
thermodynamics. Okay, so then in 1911, this guy wants to sort of say, okay, this plum pudding model, let me probe it, and he starts shooting little uh, little alpha particles, which
Alpha
today
particles.
yes, so we know them today to be uh,
Helium, right?
helium nuclei, right? Yeah, so
Yeah.
there's two protons, but he didn't know that. He just thought they were just infinitely small things that he could throw at an atom.
Mm-hmm.
And they knew atom was about 10 to the minus 10 meters big, but they didn't know they thought it was like a continuous thing.
Yeah.
And so he wanted to know where the positive charges inside the atom were. And he said, are they all in the center? Are they sort of spread out? Are they spread out evenly? Um, it's like what geologists do with, if you want to find out what the ground is like under your house, right?
Yeah.
You take measure. Is there a pocket of gas? Is there oil down there? Is there an underwater stream, or is it all solid granite? Right? You
Mm-hmm.
you want to find out. So that's what they wanted to do. They wanted to find out how atoms were constructed. So you start, poking at it with alpha particles, and it turns out. So um, he had a grad student named Geiger, Franz Geiger, and then this undergraduate, not much older than you, name of Marsden comes along, and
Mm-hmm.
he's a student who's got a scholarship that he says, I'm a student who needs a research position, so give me a research position, give me something to do.
Yeah.
So they don't have anything for him to do actually. So he says, okay, I'm shooting these alpha particles through atoms, basically a piece of gold foil, and they're going right through. Why don't you look to see if some of them bounce back at large angles?
Mm-hmm.
You know, I mean, this is silly, right? They're not, but he just
Yeah.
needed, like, it was like make work for a kid, right? And what Marston found is that, yeah, some of them, 1 in 1,000, 1 in 10,000 did bounce back. I mean, so he starts measuring at what angles. I mean, usually if it was a cotton candy thing, it was if the atom was a blob of cotton candy with raisins around it. You don't really expect, and you shoot, these alpha particles are like shooting a rifle bullet
Mm-hmm.
through cotton candy.
Yeah.
You don't expect the cotton candy to deflect the bullet, right? You expect it
Yeah.
to go straight through. If there's like a little blob of cotton candy that's slightly thicker in the center, then maybe it'll deflect it, half a degree or something, right? So that's kind of the thing they were expecting, right?
Mm-hmm.
What Marsden found is that sometimes they bounce back at, 90 degrees or, 160, like big angles.
Yeah. Relatively large angles. Yeah.
Yeah. So now put yourself in their shoes. Okay. Either this kid is, uh, you know, nuts making stuff up, or something weird is going on. So what they did was they played games where they took away the alpha particle source and say, "Oh, do you still see something?" And he's like, "No." And then they put it back, and then they of course redid it, and anyway, they established that it was really happening. So Rutherford, being uh, uh, physicist, he said, "Okay, the only way I can, you need, if you have a rifle bullet
Yeah.
and you fire it at a piece of cotton candy and it scatters off at 90 degrees, your first thought is like there must be something really, really, really dense
Mm-hmm.
inside my cotton candy, right?
Yeah.
Cotton candy cannot uh, deflect rifle bullets.
Yeah.
So this eventually leads to what we call the solar system model of the atom,
The
which,
solar system model. Okay.
yeah. So now the atom is no longer cotton candy with raisins stuck on it. It's a tiny little nucleus where all the positive charges and electrons sort of orbiting outside. And this is the atom. This is the model of the atom you're familiar with from chemistry class or something, right?
Mm-hmm.
The electron cloud.
Electron cloud model. Yeah.
Yes, and uh, and the nucleus of the center. Now, the atom, I said the whole atom was like 10 to the minus 10 meters, right?
Mm-hmm.
Okay, so now 10 to the minus 10 meters. Now I got something really, really tiny inside. Now, do you know how big a nucleus is compared to the whole atom? This place where the positive charges are. It used to be
Um.
the entire size, right? It used to be cotton candy, the size of the atom, but that's not true anymore. That all that positive charge that we assumed was, spread out over the entire atom is now punched into one tiny little place. If you were to blow the atom up to the size of Yankee Stadium, so imagine the atom, but you've expanded to the size of Yankee Stadium.
Mm-hmm.
The nucleus, all the positive charge is a blueberry on second base. Okay, it's
Mm-hmm.
really,
Wow.
really compact. So it's like 10 to
Really
the
small.
minus.
Yeah.
Yeah, so it's you go from 10 to the minus 10 meters, which is the size of the atom,
Mm-hmm.
to 10 to the minus 15 meters, which is the size of the nucleus. Okay, so Rutherford didn't have enough. His rifle bullets were not good enough to find. So he said, look, it can't be cotton candy. Okay, there's a lot of empty space here. My rifle bullets, most of my rifle bullets just go straight through, but occasionally, 1 in 10,000, they get very close to all this positive charge. And you know how electric charges work, right? There's
Yeah.
Coulomb force, right?
Mm-hmm.
K Q1 Q2 over R squared.
Yeah.
Now, if R squared is really, really small, if R is,
Yeah.
you know,
The
10
electric
to
force
the
is really large.
yeah, so let's say it's at 2 times 10 to the minus 15 meters or something, right? You're getting really close to it. The electric force is very, very, electric field is huge.
Yeah.
So your alpha particle feels a huge tug, and it just does a flyby. It just like a meteor around the sun. Whoop,
Yeah.
right?
Repels it. Yep.
Yeah. Yeah, either attracts or repels. It doesn't, but yeah, it but the forces, there's a huge force. So Rutherford was looking for some way to impart a huge force enough to change the trajectory of this alpha particle, right?
Mm-hmm.
And he found it. He said, look, I mean, all the positive charge is now in this tiny little packet at the center,
Yeah.
and the rest of the atom is completely empty space until you get out to the electron cloud. So in your Yankee Stadium model, the electrons are, you know, running around patrolling the bleachers,
Mm-hmm.
right? And your and you know or the parking lot, right?
Yeah.
In the bigger atoms, and your nucleus is like this tiny little thing, but huge amount of positive charge right at the
Yeah.
center.
And really
That's
dense. Yeah.
really dense. Yeah. So nuclear matter is like the densest thing we
Yeah.
have. I mean,
Yeah.
it's you can get stars made of neutron stars and all, but they're really dense. Um,
Yeah. It's really
and anyway,
interesting
so
that.
that's the model of the atom we have. And then well, okay, then the question is, what's that made of? And so for a while there, that was it, right?
Mm-hmm.
Fine, we change our, nothing else really changes, because now we know what the electrons aren't stuck on the atom like raisins on cotton candy. They're
Yeah.
actually in orbit
Orbit around. Yeah.
around. Yeah, so you got the positive thing, you got the atom, the electric field causes a force, and so
Mm-hmm.
it's just like the Earth going around the sun,
Yeah.
right?
And
Except it's
centripetal
gravitational
motion.
force. Yeah,
Yeah.
it's instead of gravitational. Yeah, it's the whole mv squared over r. Blah
Yeah.
blah blah.
Mm-hmm.
Right. Okay. Here's the problem. So now we're in the 1920s or something, right?
Yeah.
And the problem is, uh, the Earth going around the sun is not a problem. The Earth is neutral. The sun is neutral. The Earth can stay in its orbit for billions of years, no problem.
Mm-hmm.
The electron. So let's take the hydrogen atom. You got one proton,
Yeah.
one proton.
Proton. Yeah.
Electrons going. The electrons going round and round and round. And if you're a 19th century physicist, you can solve that, right? It's exactly the same math, right? Instead of capital G M1 M2 over R squared, which Earth Sun, it's K Q1 Q2 over R
Q2 over
squared,
R
right?
squared. Yeah.
Yeah, right. So same thing, but other than that, you got the charge, you got the charge. The trouble is, if you're a 19th century physicist or early 20th century physicist, one thing that if a charged particle is accelerating,
Mm-hmm.
okay, and
Yeah.
remember, anything that's going around in a circle has an acceleration towards the center,
Yeah.
right?
Centripetal acceleration. Yep.
Yep, yeah. So centripetal acceleration, right? And what we know, what Maxwell tells us, is that if you have a charged particle that's accelerating, it radiates. Not only do we know
Radiates.
that, we use that. Okay,
Mm-hmm.
that's what radio is. The radio works. You have an antenna. If you open up your cell phone, there's a strip of copper running along the side of your cell phone, and
Yep.
it's basically a racetrack
Mm-hmm.
for electrons going. It's the electrons go at some megahertz, millions of times a second, and it creates radio waves. You
Mm-hmm.
know, those they radiate energy, and then your cell tower or whatever picks it up. And but anyways, you can't have the Earth Sun system in the atom, because that electron will lose energy, because
Yep.
any charged particle that's accelerating is also giving off energy. So it should and that's one of the when we teach quantum mechanics or electrodynamics, that's one of the questions we have students solve, is how long would it take for the hydrogen atom to just poof, you know, disintegrate. The electron
Mm-hmm.
should just spiral in and hit the nucleus, hit the proton.
Mm-hmm.
So the hydrogen atom, by 19th century rules, is unstable,
Yeah.
right? In
Mm-hmm.
some short amount of time, actually depressingly short amount of time, all atoms should disintegrate. The atom should not exist. Okay,
Mm-hmm.
because rather than raisins stuck on cotton candy, now we've got a planet going around the sun kind of thing. But instead of a planet, it's a charged particle. It's an electron.
Yeah.
And unlike planets, electrons have to radiate when they're going around in a circle. And that's it. That's the death knell. You radiate, you lose energy, you spiral in.
Mm-hmm.
So now we're this is a big problem. This because Rutherford says no, that's the picture I got, and then everybody else says no, but Maxwell says it can't happen. I mean, something has to be protecting the electron from crashing into the thing,
I'm
right?
crashing
So
into nucleus. Yeah.
yeah. So along comes this guy called Bohr, Niels Bohr,
Mm-hmm.
and I don't know if you've heard of him.
Yeah, I have.
Yeah. So Niels Bohr says, dude, this is what we're gonna do. Okay. We're gonna use we're gonna use something called wave. So if the electron is a particle, like a planet going around the sun, yeah, then there's
Mm-hmm.
nothing to stop it from radiating. But what if the electron is not a particle but a wave? Okay.
A wave. Yeah.
Now, yeah, if you've ever played a guitar or a piano or something, then you know that if you have a length of string or a certain size, there's a certain harmonic you can play on it, right? You can so
Mm-hmm.
if you have a guitar string that's tuned to C, you can play C on it, but you can't play A or G or any other note, right?
Yeah.
You can put your thumb on it and change the length of the string, and you can play other notes. But a string of a given size can play one harmonic. It can play the second harmonic, the higher pitch of that same note. It can play three, but there are certain waves, certain standing waves that can fit on a certain sized piece of string, right?
Yep.
Does that make sense?
Yeah.
Right? Yeah. So if you look at a piece of string and you pluck it, it goes twing. But if you know the size of the string and the tension in the string and the mass of the string, you can predict what note you will
What
play,
note will play? Yeah.
right? And it depends on the size. Okay, it depends on the size of the string.
Mm-hmm.
So that's Bohr's thing. Bohr says, look, what if the orbits. So what Bohr is trying to show is that so hydrogen. The other thing with the hydrogen atom was if you heated up a hydrogen atom, it would emit light, but it would and this from chemistry, right? Atoms have certain orbitals, right? You've got the
Yeah.
1s, you got the 2s, you got the 2p,
Mm-hmm.
3s, and all that.
Yeah.
So and as electrons jump between them, they give off certain. Have you seen that picture in your chemistry class? The spectrum of light that that hydrogen gives off, or all atoms give off, right? So they
Yeah.
as something goes from as an electron goes from the 2p to the 1s state, or the 3p to the 2s state, it you know if you've got a red laser,
Yeah.
that's a certain transition. So what Bohr is trying to solve is why electrons can only be in those certain. Why is it only 1s and 2s and 3s, and why isn't there a 3.5s? Why,
Mm-hmm.
I mean,
Yeah.
if I look at the Earth Sun model, the Earth isn't fixed. I can put I can put something into orbit around the sun at any radius,
Yeah.
right? As long as I give it enough centripetal force, I'm not stuck to 1s, 2s, 3s orbitals around the sun,
Mm-hmm.
right? Why am
Yeah.
I stuck to certain orbitals around the hydrogen atom? So this is the first dawning of this what's called wave particle mechanics. Okay, so he says,
Yeah.
look, sometimes the electron looks like a wave, a particle, but when it's around, in orbit around the hydrogen atom, it's actually a wave. And
Mm-hmm.
then, if you have a wave, then you see, the 1s is my fundamental wave, and the 2s is, the first excited one, and the 3s is this one, and so on.
Yeah.
You know, so those, and if on a guitar string, you can get the fundamental frequency, and you can get the second fundamental frequency, but you can't get a 1.5 frequency on on
Mm-hmm.
on a
Yeah.
so Bohr basically just uses that. He says, look, I mean, I need to figure out why certain ones are allowed and certain ones are not allowed, and the way get you know notes on a guitar string is the only picture I can do, and it seems to work, right?
Mm-hmm.
So he says, yeah, look, I mean, if and the way they do it, so this is where the word quantum comes in. So he says, what's going to happen is I'm going to say, do you know what angular momentum is?
Yeah.
Okay. So what he says is angular momentum comes in discrete chunks, right?
Okay.
So and the way to think about it is you think about money, right?
Yeah.
Now, when you have a transaction, you exchange certain amount of money, but it's quantized in pennies, right?
Yeah.
So something can cost 3.99, or it could cost 401, but it can't cost 3.99, $3.9976 right? It
Mm-hmm.
can cost $3.99, or it can cost $4.00, but it can't cost anything in the middle there, because money in the US is quantized in 1 cent,
Yeah.
right? So in order to make these, orbits, the 1s, 2s, 3s, 3p, that sort of thing, what Bohr has to do is he has to uh, posit that this thing called angular momentum, which we all know from Newtonian mechanics,
Mm-hmm.
it actually is quantized the same way money is quantized, right? And
Yeah.
money is quantized in pennies, and uh, what Bohr says is this uh, angular momentum is quantized in this thing called uh, h bar.
H
And
bar.
h
Okay.
bar, yeah, you can look it up. It's a constant. H bar is a
Yeah.
certain amount of angular momentum. It's a really tiny. It's like 10 to the minus 34 in SI units, but it's a some amount of some amount of angular momentum. And if you're transacting in angular momentum, uh, you have to exchange integer amounts of that angular momentum. So it doesn't matter if you're transacting, a trillion, or 10 to the 20, Avogadro's number of H bar. It's like if you're
Mm-hmm.
buying a house, right?
Yeah.
The fact that money is quantized in pennies doesn't really matter, right?
Mm-hmm.
But if you're buying a gumball, right, from one of
Yeah.
those gumball machines, then the fact that money is quantized, is it 3 for a nickel, or is it 7 for a dime, that kind of thing, right? That
Yeah.
matters. The quantization of money matters when you get down to low numbers of money. It
Mm-hmm.
doesn't matter when you're buying a car,
Yeah.
right? So that's basically what's happening. You know, the it's still quantized, right?
Mm-hmm.
So classical mechanics, I mean, when you shoot a projectile, when you put a satellite into orbit, whatever, there's still, I mean, you're still exchanging integer numbers of h bar,
Mm-hmm.
right?
Yeah.
But you don't care because h bar is such a tiny number. Just like when you're buying a car, you don't care about pennies because one penny
Just
is such a
small
small
the
amount
yeah.
compared to the budget. Yeah, but it is still quantized.
Mm-hmm.
All financial transactions in the U.S. are still quantized in pennies, all angular momentum transactions in the universe are still quantized in units of h bar.
H
Okay,
bar.
it's
Yeah.
just you just don't notice it at meter scales and meters and kilograms. You have to get down to atomic size things to
Mm-hmm.
actually notice. Yeah, you have to actually buy you know a gumball to notice that a penny matters.
Yeah.
So anyway, that's quantum mechanics. Okay,
Okay.
so now yeah, so now that's it's this guy Louis de Broglie, he
De
was a French,
Broglie. Yeah.
yeah, so he comes up with this, and then
Uh, yeah, all right. So de Broglie is, really early on. So this is when people are starting to get, um, you know, an idea of what's happening at the very small scale. Okay.
Mm-hmm.
And things look weird, right? And
Yeah.
and the thing to remember is uh stuff at the small scale is not weird. What's weird is that all the fuzziness at the small scale doesn't exist at the large scale. Okay. So
yeah,
like, you can throw a baseball or hammer a nail or and you don't it doesn't feel anything like what those interactions would feel like at the atomic scale. Just doesn't. Okay.
Mm-hmm.
Take my hand and slam it into the table, and my hand doesn't go through the table. Okay.
Yeah.
Now that's completely idiotically, nobody even thinks about that, right? But
Mm-hmm.
why doesn't my hand go through the table? I mean, my hand is made of atoms, right? I told you about
Yeah.
atoms. Atoms are mostly empty space. Remember, we had the Yankee Stadium analogy, right?
Yeah.
You got you got the electron cloud way out there. You took chemistry, right?
Yeah. Yeah.
You got your electron cloud way out there. You got your nucleus in the center. Most of your atom is empty space, right?
Mm-hmm.
So empty space. Table is empty space. You got two things that are mostly empty space, yet feels solid.
Mm-hmm.
So there's something going on, and so this is what these guys are struggling with, right? They're finding all this weird stuff that's completely, I mean, if you're dealing with a plum pudding model, the 19th century model of that, I mean, it makes sense. My hand is made up of, you know, skin plum pudding atoms, and the table is made up of, formica plum pudding. And plum pudding versus plum pudding. Yeah, of course. But if it's Rutherford, if it's atoms, it's the atoms you learned about in chemistry class, right?
Yep.
Almost nothing there. It's entirely empty space. And so let's keep it. And so they had to figure all that out. So it turns out that that electrons aren't really little tiny particles, nuclei. They're fuzzy. So they actually they aren't in one spot. They're waves. They're like
Mm-hmm.
waves. And it's kind of wrong to say they're waves. They're not really waves. It's just the right thing to say is, electrons are, or nuclei or protons, light, photons, whatever, they are what they are. Okay. They have properties that sometimes can be modeled by the math we developed for particles that, like if you fire a bullet into a piece of wood, right? If you've done some physics, you know how to deal with that, right? There's energy and there's momentum and vectors and all that. And you can, if I fire a gun at a certain angle, I can calculate how far it goes, et cetera, et cetera.
Yeah.
All that particle stuff that you learned in physics, you can deal with that. And sometimes electrons behave like that.
Mm-hmm.
Doesn't mean electrons are particles. The right thing to say is sometimes the math that we've developed for particles works on electrons. Sometimes the math that we developed for waves. So you strum a guitar, or you go to the ocean and watch ocean waves, or there's sound waves, People study sound waves. You know, so people are familiar with waves, but you know, in the 19th century, they know how to do. So it's wave mechanics are a little bit more complicated than particle mechanics because you know you need calculus, you know, you take double
Yeah.
derivatives. Fine, you know, still math, you know, it's just math. But people know waves. So sometimes electrons follow waves, okay? And in fact, there's a family called Thomson. And the Thomson, the father, gets a Nobel Prize for describing electrons as particles, and Thomson, the son, gets a Nobel Prize for describing electrons as waves. But electrons aren't particles or waves. They are what they are, okay? It's a subatomic particle that has its own behavior, right? It has its own rules. Sometimes the math we've developed for particles works. Sometimes the math we've developed for waves works. Sometimes, if you're talking about spin, adding spins, it's completely counterintuitive. There's nothing, I don't know if you know about electron spins, but you know, you got your, you filled orbitals, right? The 1s,
Yeah.
1s down, 2s, 2p. Electron spin has no analog in the macroscopic world, okay? Spin is just something weird. And one of my mentors used to say, you know, if you want to freak people out about quantum mechanics, forget about particle wave duality. Teach them how to add spins, okay? Because spins make no sense whatsoever. So, you know, the bottom line is that the subatomic world is just completely different from, you know, what your eyes and ears and touch have trained you to think the universe behaves like. The universe does not behave that. Okay? Our eyes, ears, you know, touch, taste, smell, and our senses were developed, you know, for meter scale. You know, we needed to run away from predators and pick fruits and berries and you know, I mean, on the savannah, that's what human senses developed for. We were not, I mean, there was no advantage to our ancestors being aware of quantum mechanical phenomena. So we don't, so we need, so you need instruments. But once you start getting instruments of the right precision, it's really easy to see that, you know, you don't really, I mean, we have undergraduates, you know, junior, I mean, you know, the fact that the quantum world is, you know, has extra stuff in it, has fuzziness in it, pretty easy to experimentally discover. It's not that hard. Okay, people did that in the, you know, between World War I and World War II. Okay, I mean, you know, this is most of the world was still using forces to get around. All right, I mean, it's the problem happens is, like most problems, is you know, everybody wants to believe their senses. You know, you want, you know, it's a conceptual thing. Okay, mathematically, you know, you can write down equations that describe the way an electron moves inside a hydrogen atom, and you can calculate that out to, you know, just some, you know, 5, 6, 7 decimal places. I mean, more precision than you'll ever need, right? You can describe how what are these bonds? Ionic bonds, covalent bonds, you know, between atoms. It's a little bit harder to do with how nuclei behave. Nuclei do the same thing, you know. They have you know, just like you have 1s, 2s, 2p, 3s, 3p, 3d in the atoms, in how the electron nuclei within the nucleus do that too, protons, but it's harder because, you know, neutrons and protons, you know, we really don't have the kind of precision measurements at the nuclear level. With today's technology, it's getting better. Okay. Then you know, we have things like the Large Hadron Collider. We can smash the whole thing up, and then, you know, you get the quarks, the things, you know, and you know, but those are what, you know, that doesn't help you study nuclear structures. That helps you basically. That's like, you know, studying electrons by themselves. That's like, zapping your hydrogen atom so hard that the electrons fly off,
Mm-hmm.
the proton flies off, but it doesn't help you study the structure of hydrogen atom. Right? So we can do that with nuclei. We can break it apart and study the individual pieces, but it's hard to study nuclear structure that well. That's probably in the subatomic world the toughest problem. Like,
Mm-hmm.
why doesn't a nucleus just fly apart based on the huge forces pulling? What's the push and pull of the electromagnetic force pushing it apart and the strong nuclear force keeping it together? So,
Yeah.
I mean, I would say we have about 65-70%. I mean, good enough to build, nuclear power plants and weapons and stuff, but not nearly as good as we have the understanding of atoms and molecules.
Mm-hmm.
Okay.
So obviously in the nucleus you have protons and their same charges, so their forces are repelling each other. So
the electromagnetic force is pulling them apart, right?
yeah. So what forces in the nucleus are like keeping the
So
same
that's
structure
another
together?
force. So it's called the strong nuclear force. Okay, so there's two kinds of nuclear forces. There's the weak nuclear force, which can change a neutron into a proton. Okay,
Mm-hmm.
it's responsible for radioactive decay. It's actually related to the electromagnetic force. So it's basically, we consider it part of the electromagnetic force. Some people we call it the electroweak force. But the strong nuclear force is really responsible for holding the nucleus together in spite of the fact that the electromagnetic force is trying to push it apart. So it has to be really, really. So the way you want to think about it is, think about if you have two magnets, right?
Yeah.
And you know how if you have the same pole, you might have tried it, like you bring the magnets together and they're pushing apart. I mean, it gets harder and harder to bring the magnets together as you bring them closer, right?
Yeah.
Now imagine the magnets are coated with Velcro. Okay.
Okay.
So it's harder, but then the Velcro catches when you get them really close, and then they stick together. So the strong nuclear force is like the Velcro.
It's like the Velcro, yeah.
Yeah, so it's really, really strong, but it's really, really short range. Okay.
Mm-hmm.
So the strong nuclear force doesn't really become effective until basically the protons and neutrons are touching.
Mm-hmm. Okay.
I mean, it's like Velcro. It's very much like Velcro. It's really strong. If you've ever had Velcro shoes, or you know what I'm talking about, Velcro is really, really strong.
Yeah.
It's holding up your Easy Pass on your windshield, and it's been there for 5 years, and
Mm-hmm.
the Easy Pass hasn't fallen off, right? That's really strong. Try to rip off your Easy Pass, see how strong, right? But you pull it apart just a little bit, and it's not there at all, right? The electromagnetic force, on the other hand, is long range. I mean, you can have two electrons at opposite sides of the universe, and they'll still feel a repulsive force. I mean, very, very weak. It goes down as 1/r².
Yeah.
But it's still effective at long range. It's not, so the electromagnetic force goes down as 1/r², 1/distance squared, whereas the strong nuclear force goes down as like exponential, e to the minus r over a Fermi, basically. So it just basically, by the time you get down, you get a 1 Fermi or 2 Fermi away, it's zero. There's it's not holding anything together. So, but the interesting about the strong nuclear force is that both neutrons and protons feel it. Okay.
Okay. Yeah.
The magnetic force, only the protons feel it.
Only the protons. Yeah.
Yeah, because neutrons are neutral.
Mm-hmm.
And now you can see, that's why how many protons and neutrons inside helium nucleus?
There's two.
2 protons and
2 protons, 2 neutrons.
right. So you can't just have 2 protons because the strong nuclear force isn't strong enough.
Yeah.
But you add the 2 neutrons, Now you got 4 guys that are feeling the strong attraction,
Mm-hmm.
and only 2 guys that are feeling the
The
electromagnetic
repulsion from, yeah.
right? So the helium nucleus is one of the most stable nuclei we know,
Mm-hmm.
right? It's pretty stable out there. It's the alpha particle,
The
right?
alpha particle, yeah.
Right. The most stable nucleus we know, I mean, as you would imagine, if you get the same numbers of neutrons and protons. So if you look at your periodic table
Mm-hmm.
and you look at all the elements, they roughly have the same number of neutrons and protons. And
Mm-hmm.
when you start getting an imbalance, you start getting into guys that like to decay. So you look at uranium-238, that's a pretty stable guy. Uranium-238 lives for billions of years, right?
Yeah.
But then you look at some of these other isotopes that have fewer neutrons in them, like uranium-235 or something lower, and those guys decay faster. Oof, they're gone. Okay. They're radioactive. Why are they radioactive? Because they don't have enough neutrons. So the electromagnetic force wins.
Oh, that makes sense. Yeah.
Yeah, right. So to take a look at look at your periodic table. You probably got one somewhere in your school, probably on the wall of your science lab, right?
Yeah.
Yeah. Look at it and just count up the number of neutrons and protons. They're not going to be exactly alike, but pretty much all the stable elements have roughly the same number of neutrons and protons. Because you got the
Yeah.
protons pushing them. The protons give you the atomic number, right? The protons tell
Yeah.
you
Yeah.
the, like what charge you have and how many electrons you have. And the number of electrons tells you what kind of chemistry you do, right?
Yeah. So then with unstable nucleus, you start reaching a state where there are more protons than neutrons, and then
You meant more
their
protons.
and then their
Exactly.
electrostatic force
You can
repulsion
also
starts.
have a nuclei that have more neutrons than protons, in which case, yeah, they're also not happy. The happiest nucleus, the most stable guy, is iron.
Iron. Yeah.
Iron, yeah. So what happens in the long term is you got the light guys, you got the hydrogens and all that, and
Mm-hmm.
sun burns hydrogen. So you push hydrogens. A hydrogen is just a proton, right?
Yeah.
You put 2 hydrogens together, eventually, you overcome the electromagnetic repulsion, and the 2 protons touch each other, but they're not going to stick together because there's not enough strong force. But if you get 2 other hydrogens and they undergo the weak decay, and those protons turn into neutrons,
Mm-hmm.
then you get 2 neutrons, 2 protons, and all of a sudden you've got helium. And that's actually what's happening inside the sun. The gravity is so immense at the center of the sun that you're getting 4 hydrogens,
Mm-hmm.
4 protons, basically. The 2 of them are turning into neutrons via the weak nuclear decay.
Yeah.
And then you got the 2 neutrons and 2 protons, and it's turning into helium. So the sun is essentially burning hydrogen, turning it into helium.
Oh, wow.
Right. So then you get a ball. So you wait a few billion years, you get a ball of helium, right?
Yeah.
And then there's immense gravity, and our sun basically stops. Our sun's not big enough to have gravity to turn helium into anything else.
Mm-hmm.
But if the sun was bigger, then you could get helium burning. So helium can turn into, there's silicon and carbon, oxygen. So basically you get all these shells where nuclear synthesis is happening. And this keeps going on. You get higher and higher, you just keep marching up the periodic table.
Yep.
Yeah, until you get to iron. And so you say, what the heck is so special about iron? So what happens if you get a big enough sun, something like, that at the Chandrasekhar limit, which is like 3 solar masses, right? You get a big dude, right? You get a big sun.
Yeah.
And, it starts cranking up all these heavier elements, right? Until it's basically a big ball of iron.
Mm-hmm.
Right? And then it starts cranking down, because the gravity's still working, right? But the trouble is, all the nuclei that are above iron on the periodic table, and you can check your periodic table to see which one of those are, they're not as tightly bound. So they, nothing heavier than iron wants to burn. Iron does not want to burn and make heavier elements. So all the lighter elements want to fuse together and make iron. All the heavier elements want to break apart and become lighter elements. Okay, so iron is like the peak of the happy nucleus chart.
Okay, yeah, that makes sense.
So that's it. So that's so once you get a big sun made of iron, it's basically finished all the fusion it can do, so it can't burn anymore. You get a big ball of iron, and then it cannot stop gravity from pushing it closer and closer, right?
Yeah.
The sun and all these other suns, they have fusion happening. So the fusion energy is pushing outwards and the gravity is pushing inward. That's why the sun is stable. It's going to be stable for another 5 billion. It's been burning for about 5 billion years. It's going to be burning another 5 billion years. And then it'll be full of helium, and it's not, gravity wins. It's not big enough to support helium burning. It might be, but basically at some point it's going to, it's going to stop burning.
Stop burning.
And
Yeah.
it'll just collapse. And our sun will turn into what's called a white dwarf. It'll just be a ball of atoms and electrons. But if it was strong, so what happens in a bigger star is it can actually push the electrons into the protons and turn them into neutrons, like reverse weak decay. So like I said, a weak decay turns neutrons into protons and electrons.
Yeah.
Reverse weak decay, gravity just pushes those electrons back into your protons and so now you have a sun-sized ball of neutrons. Actually, it's not sun-sized, it's much smaller. And that happens in a supernova. So that's what's called a supernova. So that happens very explosively. Like a big sun, something the size of 3 suns collapses into like a few kilometers, the size of Edison, New Jersey. Yeah.
Yeah.
Right. So there you go. So that's a neutron star, right? So our sun will end up, collapsing to something the size of, Earth or Mars. And then eventually the fact that you can't push 2 electrons into the same space will keep it from collapsing further. But a neutron star keeps going until it gets to the size of, a few kilometers. That's a neutron star. So the whole thing. And then the stars that are even bigger, even the neutron pressure isn't, so those collapse into a black hole. So that limit where that happens is called the Chandrasekhar.
Okay. Yeah.
So yeah. So that's basically, yeah. So there are neutron stars out there. You can't see them except in high frequency, because they're not visible and they're not burning and putting out visible light. But there's plenty of neutron stars out there. Our sun will never become a neutron star because it's not big enough.
Okay, so just to recap, so electrons, they can get pushed into protons to do like sort of a reverse weak
reverse
decay.
Decay, right? Yeah. And then became neutrons. Yeah. I mean,
the neutrons
all it takes
push
is
into each other. Yeah.
Yeah, it just takes a lot of gravity. But a big star has a lot of mass, so that's a lot of gravity.
Yeah.
So gravity is relentless. In the end, gravity wins.
Yeah.
So you can burn your hydrogen or helium. You can burn your low mass fuel for as long a few billion years. But in the end, gravity is going to win. With our sun, gravity is going to turn it into a white dwarf. With bigger suns, it turn it into neutron stars. With even bigger suns, it turns them into black holes. In the end, gravity always wins.
Yeah.
That's pretty much, yeah.
That's a universal fact. Okay.
That's yeah. And so of all the forces, the electromagnetic force is the one we understand the best, or the electroweak force we understand the best. The strong force, we're getting a handle on it. The machines like the Large Hadron Collider are helping us.
Yeah.
And I mean, basically the understanding of the strong force today is better than it was, when I was a student. So it's getting a little better. Gravity, we don't understand really at all. We don't even have a quantum theory of gravity. I mean, we know there has to be, particles that transmit gravity, just like particles, definitely know the particles that transmit the electromagnetic force.
Yeah.
They're, called photons. And we see the particle nature of the electromagnetic force. We can see the particle nature of weak nuclear force. We can see the particle nature of the strong nuclear force. We cannot see the particle nature of the gravitational force. We just can't. In the last few years, I think, basically since you've been in high school, we've begun to see the wave nature of the gravitational force. So with gravity, we are basically where the late 19th century Maxwell and all were with electromagnetism. We're beginning to see the wave nature of things, but we haven't seen the particle nature of gravity. It's just, that's sort of the final thing. If we can figure out how gravity works in the quantum world, that would be, it's called a, grand unification theory. It'll unify gravity with quantum mechanics, but we haven't gotten there. That's pretty much the entire thrust of all of particle physics right now.
So if we find the answer to that, so the particle properties of gravity, what future future theories could that lead to, or maybe what
so if we do actually solve the gravitational the conundrum of quantum gravity, it's called, well, okay, I can't say what it would be because I don't know what the theory will look like.
So but would it
probably, just like quantum mechanics completely had us rethink the universe, right? I mean, as one of my colleagues here said, objective reality is an emergent phenomenon. It emerges out of the fuzziness out of the subatomic world. What we think is solid and real is really just fuzzy math at the subatomic realm. So I suspect it's going to help, quantum gravity will have us question everything, let me think about it. So, okay, so what do you take for granted? Time and space, right? Space, maybe if you know relativity. But, I think if gravity is quantized, that stuff has to be quantized too, right? Time has to be quantized, space-time has to be quantized. I mean, what is distance? I mean, what do we mean by, two things are a meter apart? Newton just said, oh, I'm going to define something called distance. I'm going to define something called time. And then I'm going to just write, x as a function of t, x equals x naught plus v naught t plus 1/2 at squared. And you can keep going with that series, but we stopped there. But that's just a Taylor series, right? But he had to start with distance and time and then work up. But maybe distance and time are not real. Maybe distance is just how our brains perceive, quantum entanglement. Two things that are entangled are perceived, they're very entangled, our brains perceive them as close together in distance. If they're not that entangled, we perceive them as, far away. And maybe, who knows? I'm just making stuff up now, but we'll have to rethink once we have a full theory. I think we'll figure out what this universe actually is, rather than this thing in the universe and that thing in the universe and that other thing in the universe. You
Yeah.
know,
So I'll come to
the
one.
entire construct. Yeah.
You get a whole concept. Yeah.
Yeah, because we'll have one theory for the whole thing. Right now we've got roughly 4 theories.
Mm-hmm.
Right. And then based on those 4 theories, we make other theories like chemistry and biology and all that, which are theories that are built on top of, you know, the underlying theories. But we don't have the one theory that's under everything, right? And our feeling is quantum gravity is that one theory.
Yeah.
Like there was one force, you know, there was one thing at the beginning that, you know, and then as things got colder and colder, as the universe expanded, it started looking like 4 different forces,
Mm-hmm.
right? But so it's called grand unification. Like all the forces that we've measured, you know, doing different things at the early universe. So one of the ways you can think of the Large Hadron Collider is an early universe simulator.
Mm-hmm.
Right? We're simulating the conditions at the Big Bang, or as very close to it as we can get. So what we should be seeing once we get close enough is the forces that were active then. And so far we haven't, we still see 4 separate forces.
Mm-hmm.
Separate forces. I mean, we've seen the unification of electricity and magnetism. Maxwell did that in the 19th century. Then the electromagnetism, we saw the unification of electromagnetism and the weak nuclear force in the 60s.
Yep.
But the strong nuclear force and the gravitational force are still, they're still separate forces.
Yeah.
What we would expect, we would hope for, is all forces. Look, you know, there's some grand unified force,
Mm-hmm.
and then when you run the universe, it gets bigger and bigger and colder and colder. Oh, now it starts. Oh, look, this part of the force looks like electromagnetism, and this part of the force looks like gravity. This part of the force looks like the strong nuclear force. But you know, in the early universe, they were all the same force. And we sort of know that just based on symmetry and aesthetic principles.
Mm-hmm.
But we don't know when we may not in 2023, we may not even have the math for it.
Yeah.
You know, it's like, you know, why didn't Galileo come up with Maxwell's equation? They didn't have vector, you know, the calculus for it.
Mm-hmm.
Right? I mean,
Yeah.
they probably had enough, you know, they could probably have done the experiments, but you know, I mean, sometimes you just need mathematical sophistication that I think maybe we don't have yet. We need to invent the math, the way Newton invented calculus.
Mm-hmm.
You know, then people started to understand. And now you guys learn calculus in high school, right?
Yeah.
Right? I mean, at the time, it was cutting edge physics. It was cutting edge math.
Mm-hmm.
Right? And then same thing, like I was mentioning spins, we needed something called group theory. Okay, so these are just adding and subtracting matrix. I don't know if you've had linear algebra.
No.
Well, yeah, so that's undergraduate, you know, your first, second year of college. If you go into science and math, you know, you learn what matrices are and how to multiply, you know, and
Yeah.
that, you know, but at the time it was considered very, very, you know, grad school level stuff.
Mm-hmm.
And so what happens is you know, these mathematical concepts exist, or they get invented, and then they sort of trickle down. I mean, I'm sure, you know, in a few years, you know, all the stuff that the physicists are working on and you know, that work like group theory and, you know, matrices and all that, it'll, you know, high school students will be learning it.
Yeah.
You know, it eventually just all trickles down. I mean, right now, I think you'll probably learn it in your sophomore year of college, but There's no reason. I mean, there are students who are learning linear algebra in high school already. So
Yeah, probably.
it's not that, you know. I mean, I'm sure there's Khan Academy videos on it.
Yeah, probably.
Yeah, you know, so, yeah. But yeah, so none of the math is really that difficult. It's just it's the, you know, it's the weirdness, because, and it's not that the stuff is weird, it's that our brains are trained to think of, you know, things on the size of baseballs and coffee
Yeah,
cups,
so it makes
you
like
know,
such
or
a
not.
microscopic
Yeah,
size seem so strange.
yeah. So yeah, so I really just like calling the quantum world strange, because it's not, you know, it is what it is. It's to, you know, if you were looking at the evolution of the universe, we would be strange, you know, these lumbering beasts that
Yeah.
have no quantum fuzziness that, you know, detectable, you know.
Mm-hmm.
And yeah, it's just that our eyes and ears develop to see big things.
Mm-hmm.
Right, that's all it is.
Yep.
Yeah, I mean, you need instruments to see, but yeah, hooray, instruments. We have instruments.
Yeah.
Yeah.
Okay. I think that's a good place to stop.
Alrighty.